Welcome back to the, meanwhile, fifth video about the MMC5983, yeah, that rhymes, MA, 3-axis magnetic sensor. In the previous video, we talked mainly about the different bandwidth settings, filtering settings for that thing and the associated noise. We also implemented the continuous measurement mode of that thing. Card here, link in the description. Now we just, move on with the rest of the configuration options that thing offers. Enjoy! There has been a slight update to my register cheat sheet here, and that's in regard to the color coding. There were two changes, but the most important change for now is that yellow now has a different meaning, and it means right only. Yeah, it turns out you cannot really read the internal control registers. If you try to read them via I2C, independent from which register you're trying to read, you get the same fixed bit pattern back and not the real content of the registers. So I've updated the cheat sheet accordingly. And in the download link, in the description, you will find the new version. Anyways, let's talk now about these two configuration bits in the internal control register 3. And that's STENM, EN for enable and M for minus. Enabled negative current / field. Yeah, we will have to verify that in a second. And then we have here a bit called ST. I have no idea what the ST is for, really. EN, enable P, positive. Enable a positive current field. The thing is, our little chip here has a built-in coil, so it can create an internal magnetic field, which we then can pick up with our 3 sensors on the 3 axis. Let's implement that. Like for the continuous measurement stuff we did in the previous video, it makes no sense to handle these 2 bits independent. Either you will have a positive current or a negative current through that coil. So we put these 2 bits here into an enum magnetic field, which is either off, that means all bits are 0, or we are positive, whatever that means. Then this bit is set, or it's negative, then that bit is set. Of course, we have, like for the bandwidth and the continuous measurement, related set magnetic field method here, which gets as an argument that enum magnetic field. Finally, in the header file, I define here a constant expression with those 2 bits here as a bit mask to use later in my implementation. So in the control register 2, the ST enable X bits. And then in my CPP file, I have the implementation for set magnetic field. Really nothing new. We have done this 2 times before now. So I take the contents of my control register 2, I binary end that with the complement of my bit mask here, masking out these 2 bits, and then I binary all that with my magnetic field argument of the function, and I assign that to my control register 3. Now, to test that in the sketch itself, I don't think I changed anything in setup. Please remember, we are currently in continuous measurement mode, taking 20 measurements per second. And then in the loop, I reactivated my switcheroo thing here with a counter. Also used before. But this time, if my count is 0 here, I'm setting the magnetic field to off for a duration of 100 loops, and then I set the magnetic field to positive, and then after 50 more loops I'm setting it to negative, and after 200 loops, loop 100 milliseconds, Then I reset my count to 0 and we begin anew. Take magnetic field measurement is still commented out. We are in automatic measurement mode. And after a delay of 100 milliseconds, I read my axis output and I print out my axis in 18-bit, all three of them, X, Y, and Z, in milligauss, so multiplied by 1000. Yeah, 4 digits after the decimal point. And that's it. Let's have a look at the serial plotter. And that's what's happening here. So I have here my long shoulder, yeah, over 200 loops or aboutish 20 seconds. Then comes positive, which obviously is not positive, but it's going down. So we have to correct the code there. And then comes negative, and then comes my magnetic field off shoulder again. Interesting thing here to notice is that obviously that magnetic field is not picked up at the same level on all three sensors. So let's first go for the blue sensor, and I'm trying to align that shoulder roughly to 0. Yeah, we are at 0, and now we wait a little bit. So the negative value, if I should estimate that, this is 900, about 1000 milliteslas, milligauss, excuse me. And positive, it's about the same. So here is 900, so 1000, 1500. It really doesn't matter. I just want to have a rough estimate. Let's do that too for red, the y-axis. I have to wait until we're at the 0 shoulder again. And let's just rotate until y is on 0. Okay, that's far less. If I should need to estimate that, so here's 400, let's say 200 milliteslas. Maybe a bit more. Let's say 300 milliteslas. And now for green Z, this will be a little bit trickier. Adjusting. Should wait until I'm at the 0 again. I have to hold that, so it will hard for me to actually move the mouse and show you. Oh, that's even less, huh? What did we say? This is 400. This is, that's probably 200 milliteslas. Okay, 200 milliteslas. I think I've got everything I need. Okay, with that under our belt, so I have rewritten the description here. So we are enabling a positive, P plus, respectively negative, M minus current through a coil. That's the flags ST enable P for positive and M for negative bits. The result, this will result in a positive, for the ST, E, and M, so minus bit, and negative for the STEN positive bit magnetic field. And the order of magnitude of the magnetic field, as we've seen, is for the x-axis plus minus 1000 milligauss. It's Gauss, okay. Y-axis plus minus 300, Z-axis plus minus 200. Now, why is that all different? It's different because our sensors have a different orientation, all three, and I'm sure there's only one coil in there. So it depends on which angle the field lines from the coil cross through our sensors, as how much of that magnetic field we are generating is really picked up by each sensor. Yeah. And now this looks much better here on the serial plotter. So we have here our zero shoulder, and then we have a positive artificial magnetic field here, which drives our values up, and this is followed by a negative magnetic field here, which drives our values down, and then we have a zero shoulder. Great. So, what can you do with that feature? I mean, again, here I won't read out both of them for the enable positive and enable minus, not negative, but minus. But it says writing one will apply an extra current flowing from the positive end to the negative end of an internal coil, whatever positive and the negative end of a coil is, and result in an extra magnetic field. And here is it is, of course, from the negative end to the positive end. Yeah, we know now in which direction the generated magnetic field goes. That's the important part. And then this feature can be used to check whether the sensor has been saturated. That is, an external magnetic field is applied that exceeds the range of our sensor. But I would argue that doesn't work. Our measurement range is between plus 8 Gauss and minus 8 Gauss, plus some change. Card here, link in the description. And we apply an external field of, let's say, 10 Gauss. Then, of course, we'll still get a readout of 8 Gauss because, yeah, our sensor is saturated. We cannot read more than 8 Gauss. But in that case, applying through the coils minus 1 Gauss field, reducing effectively the magnetic strength to 9 Gauss, or even applying a positive 1 Gauss here, so extending that out here to 11 Gauss, doesn't change anything for us. We would still read out 8 Gauss. Okay, so that's not really working. There are cases in which that method would work, but if it doesn't work every time reliably, you cannot really use it to determine if your sensor is in saturation. Yeah. What you can use it for is to check if your sensor is still working at all. For example, in the setup method. Maybe we'll implement that later. Moving on to the, let's say, enable measurement done interrupt, control register 0. We've seen in the basics video, card here, link in the description, that our chip has an interrupt out pin, which is active high. That is, it goes high when we write a 1 to that bit here and a measurement has been done. It doesn't matter if it's a temperature measurement or a magnetic measurement. However, to get that interrupt line low again, you have to write, depending on what kind of measurement you have done, a 1 into the status register, either into the measurement temperature done bit or into the measurement magnetic done bit. Let's first have a look at my breadboard and then at the code. On the breadboard, I just connected here the interrupt output pin of my MMC5983MA to the digital 2 pin of my Arduino Nano Every. That's all. And yes, the output here will be only 3.3 volts, but that's enough for a digital input pin of the Nano Every to actually recognize that as a high signal. Now for the code. I defined another enum here, interrupt, which just defines that single bit here in the control 0 register, interrupt enabled, and of course also an interrupt disabled with the bit being 0. You could do that with a boolean and some more code in the implementation, but that is more readable. Then I have here two public methods, clear interrupt magnetic field and temperature, to write that one into, or the two ones respectively, into the status register. And of course we have a set interrupt method here where we can write to our internal shadow configuration register that interrupt bit set or not set, that is the interrupt enabled, disabled. In the private part of our class, we have already defined in a previous video the status register, measurement, magnetic done bit, and temperature done bit. What's new is the control register 0 interrupt measurement done enabled bit here. The implementation of the clear interrupt magnetic field and temperature commands is even simpler than for the other commands. For the other commands we have to somehow do a bit of bit banging to preserve bits in the control registers, but in the status register there are no bits to preserve. The only bit that we could preserve there is read-only anyway, so we just write the corresponding bits here to the status register. The implementation of set interrupt is completely analog to the other set methods, so I won't explain it in detail again. We just set the right bit here, our interrupt in measurement done enable bit inside the control register 0. And that brings us to our sketch where we have a new constant here, byte interrupt pin 2. Remember, I showed you I connected the interrupt output pin to our digital input pin 2 on the Arduino, and a volatile bool measurement done, which will be set by an interrupt routine. And here's that interrupt routine, which really does nothing else but setting our volatile measurement done boolean to true. In the setup function there's also something new. First I initialize that measurement done boolean to false. Then I say that my interrupt pin is an input pin, and then I attach my interrupt routine to that pin on the rising edge. So every time the interrupt output from our MMC chip goes high, the interrupt should fire. And of course I'm setting here my interrupt option to interrupt enabled. In the loop all the switcheroo stuff is commented out again. Then instead of doing a delay, we now test if our measurement done boolean has been set to true by the interrupt routine. If that's the case, then I repeat my read access output until it succeeds. If there is an error in between, I print out the error. Then that's important. I do a delay of 1 millisecond here before I call the clear interrupt magnetic field function. if that fails, I also print out a serial error, and in a while loop I repeat that until it worked. Very important, without that delay 1, the whole thing will block. And it blocks inside the wire library because somehow the communication on the I2C bus gets scrambled. I still don't know why. Maybe the chip is busy after it sent us the access output or whatever. But you need that delay of 1 milliseconds here. So this command here, which is just writing data to the chip, will not hang in the wire library. And then I reset my measurement done to false, and I print out all our access data in Gauss this time, milligauss. And here's the output on the serial monitor, and yes, the numbers are changing if I'm rotating my chip here. Anyway, let's wait a second. There it is. Still in between, I get an error when I do a read access output. 5 indicates that I do not get the full 7 bytes I requested back from the chip. Why that is, still have to investigate that. And just so you will believe that this delay 1 here, I mean, maybe we need a delay less than 1 milliseconds, but 1 millisecond works, that this delay 1 here is really required. I commented it out, and now we will have a look at the serial monitor. And of course, now it's working without the delay. I don't know why. I swear. It was blocking. Just to be clear, it is the wire library and transmission method that will block indefinitely if the slave doesn't acknowledge a transmission by pulling down the SDA line. There is no timeout or something implemented in that end transmission method. So it just hangs, and then your whole Arduino hangs, unless you implemented a watchdog, but that's for another day. I forgot to mention that new color code blue here at the start of the register. So we already have that green read-only bit here, but the blue bits in the status register, as we have seen, behave a little bit differently. You can read a status from them, if a measurement has been done, but you can also write a 1 to them, equivalent to our write 1 bits here, our command bits, to reset the measurement done interrupt logic inside the chip. So different behavior, new color code. Let's move on to the YZ inhibit and X inhibit bits here in control register 1. And these bits allow you to disable the Y and Z and the X channel. And I don't believe that here for a second, not really. So we will test that you can only disable the Y and the Z channel together. I mean, that makes absolutely no sense. So let's write some code and test that. You know the game by now. I have a new enum here, Inhibit, and it's all 0, so the default values, we inhibit no channel, then that single bit here for the X channel, and then the next 2 bits here for YZ channel, and then not supported according to the data sheet, single bits for the Y and the Z channel. As usual, we have a set inhibit public method, and I define in the private part of the class a constant here for the inhibit bits as a bit mask. Implementation of the set inhibit method is completely analog to the other set methods, so nothing new here, just setting the bits in my shadow register and assigning it to the shadow register. And within my loop, the whole switcheroo stuff here is now inside my if measurement done statement. And by the way, I extended here my counter to be an unsigned int. And here is a switch statement. And please note, throughout the code, I commented out all serial print stuff because I want to use the serial plotter. So case 0, so 0 count to 49. We inhibit no channel, then from 100 onwards, X channel, then 150 Y channel, 200 Z channel. Remember, these two are not officially supported by the datasheet. That's just a little bit experimenting. And then from 250 onwards, the X and Z, the Y and Z channel, that's supported, setting the 2 bits at once. And at 300, we revert back to the beginning. And that's how the whole thing looks on the serial monitor. Yeah, I'm just wiggling here a little bit so we see some movement. And yeah, that was Y and Z channel disabled. And now for the count of 200, we have everything enabled. I'm looking here at the beginning. And then here for the count of 50, X is disabled. And now we would have expected Y to be disabled. It's obviously not disabled. And now Z disabled. It's not disabled. But now Y and Z are both disabled. And now we have, for the count of 100, everything enabled again. So yeah, it's setting the bits differently for the Y and the Z channel is obviously not supported. Well, it's not documented and it really doesn't work. I see something. Let me pull the plug here. I probably have to zoom in the video editing, but as you can see here, the X line, if it's disabled, it's completely flat, and the Y line is completely flat, but there is some wiggle here to the Z line. So it's clearly no longer working, but it's also not 100% disabled. What can you do with that function? Honestly, I have no idea why they implemented that. Never saw that before on any 3-axis magnetic sensor. That's it for today. Yeah, it's a little bit slow going, partly because, yeah, the datasheet is not very verbose about things. Anyway, next time we will handle the last 1, 2, 3, 4, 5 configuration bits here, and this will be again about the pre-magnetization of the sensor. Yeah, we handled that in some part. Card here, link in the description. Till then, bye.